is a discussion of thermochemistry, a topic we've already done an intro. Should be pretty easy. Hi, this is a topic that we've already done before. Chapter 6, Thermochemistry. So, we want to talk about energy, the nature of energy. Energy, of course, is the capacity to do work or produce heat. And in chemistry, of course, you want to do useful work and produce heat. That which is needed to oppose natural attractions is energy. So, in general, substances may have a certain attraction for each other, that natural tendency to pull together. But energy is needed to come in and pull those attractive forces apart. The law of conservation of energy, however, remember, states that energy can be converted from one to another, but it can't be created or destroyed. So if there's a certain amount of energy that is put into the system, it has to come out of the system. The total energy content of the universe is constant. Potential energy, remember, as energy due to position or composition, whereas kinetic energy is energy of motion. And the motion of the object, and it depends on the mass of the object and its velocity. Now, you read a little bit more detail in the textbook, but that's just a quick overview. Here's an example. You notice ball A and ball B. Initially, ball A is higher than ball B. The initial position of ball A has it showing higher potential energy than ball B. Then, after A has rolled down the hill, what happened? Well, when A rolled down the hill, it obviously hit B, which then rolled up the hill. So the energy that A lost was actually gained by B. And you can see there are some other kinds of motions that could happen. Here it suggests frictional heating due to the increase of the potential energy of B. Now as you see it, B has more potential energy than A does, because it's energy of position. The topic we're going to be focusing on in this chapter is heat. Heat involves the transfer of energy between two objects because of some temperature difference. So if two objects are at the same temperature, there's not going to be any heat change. Work is force acting over a distance. I'm sure you remember from physics. These are topics that you already covered. Energy is a state function. Work and heat are not. What is a state function? We already talked about this when we did our Starbucks and thermodynamics. A state function is a property that does not depend in any way on the system's past or future. It only depends on the present state. So energy is a state function. How much energy something has. It doesn't say anything about the energy before or the energy after. It's just the energy. Work and heat, however, are not state functions. Chemical energy. Well, when we talk about chemical energy, we have to think about the system and the surroundings, the two pieces. What is the system? The system is what we're looking at. So if we're looking at like a hot cup of tea, then like this one, this is the system, part of the universe on which we wish to focus our attention. So it's the heat in the tea. The surroundings include everything else, even this computer, but of course the tea isn't that close to the computer. The surroundings could even be the cup, or my hands, or the air around the cup. That's considered the surroundings. So when we're talking about a chemical reaction, unlike the tea, which is really a physical change, we have to think about the different kinds of reactions there could be. Of course, there are endothermic and exothermic. Endothermic reactions are ones where heat is being added to the system. Heat is entering the system, absorbing energy from the surroundings in some fashion. So when I made my tea earlier, I actually had to put some hot water on the stove, and then had to heat up. That water, which came from my tap, was originally room temperature water or cold water, and then I had to add energy by turning on the stove to make it hot. So it had to absorb energy from the surroundings. So the water itself had to gain energy from the stove. That's an endothermic reaction. Exothermic is the opposite. Energy flows out of the system. So, right now, I've got some warm tea in here. The cup that holds this is getting warm. And I like that. And I'm sitting in my basement, so it helps to have a hot cup of tea. Here, energy is flowing out of the system. Now, granted, it's not a chemical reaction, but energy is involved. Energy is flowing from the hot water in the tea out to the cup, and that's what my hand's touching, and it feels warm to my hand. That's energy flowing out of the system. Remember that the energy gained by the surroundings must be equal to the energy lost by the system. So if I put in a certain amount of heat energy into the cup, it's going to be let out in the form of heat energy into the surroundings, like the cup, or the air around the cup, or my hands, that kind of thing. So let's look at different processes and classify them as exothermic or endothermic, and then we'll talk about them. All right, your hand gets cold when you touch ice. So think about that. Have a piece of ice, and we touch it, grab onto it. Our hand definitely gets cold. So think about our hand itself. Is that exothermic or endothermic? Exothermic. And you think, well, but if my hand feels cold, then why is it exothermic? Well, remember, the ice is taking energy from our hand. We are giving out heat energy. If we're giving out heat energy, how does the hand then feel? Well, it feels cold because we're sucking heat away from the hand. So the hand itself is exothermic. Of course, the melting ice, endothermic. Oops, hang on, part B. The ice gets warmer when you touch it. Well, I kind of gave it away. As the ice gets warmer, where's it getting that energy from? Endothermic, right? It has to gain energy from the surroundings. And if you're grabbing onto it, then it's from your hand. Water boils in a kettle being heated on a stove. That's what I did right before this video. Boiling water. So I got my water, put it on the stove. What's happening to it? Endothermic again. It has to take in energy to heat up. Remember, later on it's going to give it out. And then the last one, water vapor condenses on a cold pipe. So what happens there? So it was water vapor, that means water in the atmosphere. And then it condenses on a cold pipe. Sometimes you see this in weather, in the wintertime. One day it can be warm, next day it can be cold, and then you'll get condensation, like on the outside of your car window. Or if it's too cold, it'll actually freeze. But on days that are above freezing, sometimes you'll get dew. It's kind of like that, water vapor condensing on a cold pipe. So we're going from vapor to a liquid. What is that? Exothermic. It has to give out energy. Remember, water vapor has higher energy than liquid water, so it had to give out energy to become condensed, or a liquid. So exothermic. Oh, last one. Ice cream melts. How does that ice cream melt? How does it go from a solid to a liquid? Well, it must take in energy to do it. So ice cream melting is an endothermic change. Now, the law of conservation of energy is often called the first law of thermodynamics. So that's easy to remember. And the internal energy of a system is the sum of the kinetic and potential energies of all the particles in the system. That's the energy of the whole system. To change the internal energy of a system to a formula, this is it. Delta E equals Q plus W. Q is heat and W is work. And you'll read again in more detail. The sign reflects the system's point of view. So things that are endothermic, Q is positive. And for exothermic, Q is negative. However, the sign reflects the system's point of view again. The system does work on the surroundings. W is negative, and the surroundings do work on the system. W is positive. So if something is happening to the system, we add energy to it. work to it in this case. But the more important concepts are around enthalpy of formation, and delta H. We revisit state function again, which we talked about earlier. Delta H is Q at constant pressure. How do we calculate delta H? It's the difference between the products and the reactants. Like we had discussed, if we look at energy diagrams, the difference between the products and reactants is the delta H value, and it really doesn't matter the beginning or the end. It just matters the change. So let's consider the combustion of propane. Here it is, and there's the delta H value for it. Assume that all of the heat comes from the combustion of propane. Calculate delta H in which 5 grams of propane is burned in excess oxygen at constant pressure. So how do we do this particular question? Excuse me while I scratch my eye. This is a pretty easy one to do. We know that this is, and let me get the pen. We know that this is delta H is this many kilojoules for 1 mole of propane. And you might say, well, how do I know that? Well, because there's a coefficient of a 1 in front of propane. It also is for 5 moles of oxygen, 3 moles of carbon dioxide, and 4 moles of water. But here, the 5 grams of propane that they give you in the question is what we have to use. So what we need to do first is we have to, of course, to use this, we have to convert 5 grams to moles of propane using the formula mass. Then that would be for that many moles of propane. So when I did it, I said 5 moles, and I'm not, let me use correct sig figs because I tend not to do that if I'm not thinking. And from grams to moles, I got 44. Therefore, I got 0.1136 moles. And I added an extra sig fig. And this really does not look like a 0. Well, it kind of does now. So that's how many moles we're talking about. Now I could set a ratio if I wanted to. I could say if 1 mole is negative 2221 kilojoules, then 0.1136 moles is how many? And I could solve, or I could make it look more like dimensional analysis, and I could say how many kilojoules equals 0.1136 moles. In other words, I could have just continued on what I was doing above, and I know in 1 mole there's negative 2221 kilojoules, and when I work it out, I get negative 252 kilojoules. And we've done problems like this before, so pretty straightforward. Calorimetry is the science of measuring heat, and we have done this before, and we will do it again. Remember specific heat. It's the energy required to raise the temperature of 1 gram of a substance by 1 degree. Different substances have different specific heats based on the nature of that particular substance. Molar heat capacity is the energy required to raise the temperature of 1 mole of a substance by 1 degree. So that's a little bit different, because you might not have a whole mole of a substance. Specific heat is per gram, and molar heat capacity is per mole. So let's look at this situation. If 2 reactants at the same temperature are mixed and the resulting solution gets warmer, this means the reaction taking place is exothermic, of course. And an endothermic reaction cools the solution. So when we mix 2 things together, the solution gets colder because the chemicals are actually pulling the energy inward, and the surroundings feel colder. The thermometer's in the surroundings. So here's a coffee cup calorimeter made of 2 styrofoam cups. The books always talk about professional calorimeters. Every time we've ever done a calorimetry experiment, we use these 2 styrofoam cups. And sometimes students will point to errors in their lab because of the unsophisticated nature of this device. Even though it's kind of unsophisticated, it actually does a really good job. So there it is, you might remember it. The solution happens here, whatever mixture is combining, some probably water and some chemicals, and then the thermometer in there. One of the labs we'll do involves this sophisticated piece of equipment these styrofoam cups. So the energy released, here you can see their calculation is S equals M times S times delta T. We called it Q equals MC delta T. And I think if you look on your cheat sheet, I think they actually use Q equals MC delta T. If not, I think they give you the meaning of all those pieces. So you should look for it on your cheat sheet. Oh, there it is. Specific heat capacity, mass, and change in temperature. This is how we calculate heat energy. So let's look at this example. We have a 100-gram sample of water at 90, and it's added to a 100-gram sample of water at 10. The final temperature of the water is what? Well, you can solve this mathematically if you want to, but this one's kind of easy. You don't need to. So if we have equal masses of the same substance, meaning both water, we mix them together, then whatever the average of those temperatures is going to be the answer. In this case, 50 degrees. Here's another question. This is a little trickier. A 100-gram sample of water at 90 is added to a 500-gram sample of water at 10. What's the temperature going to be now? Well, let's think about it. Is it going to be between 50 and 90, 50, or between 10 and 50? Well, we can think about it this way. The 500-gram sample, whoops, calculate the final, oh, now they want you to calculate the final temperature. I thought I had my pen on. Is it not wanting to work? Let me try it again. Yeah, it was on. Anyway, the 500-gram sample of water at 10 is the one that there's 5 times as much of it. So it's going to count 5 times as much. And so, therefore, it should be between 10 and 50. Let's see. Oh, good. Now, the final temperature of the water, how are we going to do that? Well, you can use the, and I do not know why this keeps going. They say the answer is 23. You can see that. I just revealed that. I'm not sure why the pen is not working. Oh well. MC delta T equals MC delta T. We can set these two equal to each other, and we can actually figure out the final temperature of the water. There's also another way to do this one, and I can show you the shortcut in a minute. So we have a 100-gram sample of water, and the specific heat of water is 4.184, which you might remember from intro. No worries, though. I think your cheat sheet actually lists that, so you don't need to memorize it. And the sample of water is at 90. Now, in the end, that's what delta T is, the difference between the two temperatures. We don't know the final temperature, but we know 90 minus TF is going to be the number there, because the final temperature has to be lower than 90 and higher than 10. The other side we have 500, 4.184, and in this case the final temperature is going to be above 10, so we put TF minus 10. When we work it out, we get, I guess we get 23, because that's what they told me we get. Another way to think about it is this. We can think about 6 parts. There are 6 things we have to add together. One of them is worth 90, and the other one is worth 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, that's worth 10. And if we add those, 90, 100, 110, 120, 130, 140, divided by 1, 2, 3, 4, 6 things. Let's see, and I forgot to bring my calculator, so now we're going to watch and see if this works. 6 times 2 is 12. 2, bring down the 2, though this is long division. 3, 6 times 3 is 18. 2, it looks like it's 23, etc. Alas, also 23 degrees. So that actually worked pretty well. And it only works because it's a pretty easy ratio to think about. But if it wasn't the same substance, if it wasn't both water, and the numbers weren't easy, it's probably easier to use MC delta T equals MC delta T. check this one out. You have a styrofoam cup with 50 grams of water at 10. You add 50 grams of iron ball at 90 to the water. Specific heat of water is 4.18, and specific heat of iron is 0.45. Notice the unit of specific heat is joules per gram degrees Celsius, or degrees Celsius gram, either way. Now, here's one where you're going to have to do some thinking. It says the final temperature of the water is, where is it? Well, you might think, these are both the same temperature. Why don't I take the average again? Shouldn't it be, between 90 and 10? Shouldn't it be between 50? Should it be 50? Well, actually, I think it's going to be letter C, between 10 and 50. Why? Because the iron has a very low specific heat, and therefore it doesn't hold heat as well. So when it's mixed together, it's going to lose its heat really quickly, and therefore the water, which has a high specific heat, is going to take a lot of energy to heat up. So the temperature of the water in the end isn't going to be 50, which is what happened when we had water, when we mixed two things of water. To calculate this, we can again use, and here we go with the weird PowerPoint. Sorry about that. So now you see the answer is 18. How do we get it? All right, MC delta T equals MC delta T. Right, so let's take, this will be the water side, and this will be the iron side. I've got to write that or I will forget which one is which, and I'll fill in the wrong numbers, because of course there's two masses, two specific heats, etc. All right, so we have the cup has 50 grams of water. All right, and specific heat of water 4.18. Delta T. Now, the water's at 10, so the final temperature is going to be higher than 10. So it's TF minus 10. For iron, the iron is super hot, 90 degrees. It also is 50, but notice the specific heat is 0.45. That's what's going to cause the difference of TF. Here, we're going to say 90 minus TF. All right. When we calculate all that out, I believe you get 18.